I'm hoping that this microphone is better now. So I've been going over Ergorov. Maybe you spell it with Ergorov's theorem. A way of recovering almost uniform convergence from pointwise almost everywhere convergence on a finite measure space. Okay. I think that's a good way of summarizing it. So we're just going to go over it. Okay, we're going to formally state the theorem. So you have a finite measure space. We have x b mu, right? So x is some space, b is the sigma algebra on the space, mu is the measure assigned to that comes from the sigma algebra. Finite measure space means the measure of x is less than infinity. Measure of x is a finite number. Okay, so we have a sequence of measurable functions on x, and we have another measurable function on x. So we know, right, that we can, obviously, if n equals 1, f can be its own, like, then that sequence would just be like a constant sequence, essentially. But, so assume that these sequence of measurable functions converge to f pointwise almost everywhere. Almost everywhere means that there is some null set, some set of measures, 0, where this doesn't happen. It doesn't converge pointwise. It something else, right? It blows up or whatever. Then for any epsilon greater than 0, so for any epsilon greater than 0, there's a measurable set D of x such that we can make that measure is small. I'll just read the statement before I interpret it. Then for any epsilon greater than 0, there exists a measurable set D of x such that the measure of D is less than epsilon, and f converges to f, and fn converges to f uniformly on the complement of D. Okay, so the way that I see it is that this is why we call it almost uniform. So like, you can have f of n converge to f uniformly outside of some set that's getting arbitrarily small, so you can approximate a uniform convergence. And apparently this only happens for finite measure spaces that you can do this. The thing about, so eventually, okay, so what's going to happen eventually is that we're going to talk about domination theorems and theorems related to dominating convergence, where you may not have a measure space that's finite anymore, but like locally, I guess that's how I want to say it, locally there are these sets that kind of behave like you have a finite measure space, and then you can do all of the Ergorov stuff on there. And I actually have an example of this, and we'll probably talk about it in the next video. So, okay. So proof. Okay, and I've seen this proof 4 different ways now, and every one of them starts with, without loss of generality, assume that we're converging pointwise everywhere instead of almost everywhere, because we're like basically looking at stuff up to this equivalence of null sets anyway. So like, just assume that it's converging everywhere, right? So what we're trying to do, and here's how we're going to think about it categorically. And this is why I like thinking about things categorically, and I think this is why category theory makes so much sense. So we obviously are dealing with functions, right? The theorem talks about this statement on functions, and what we're trying to do is find a set. So we're going from the function, like we're going from the space of measurable functions to the space of measurable sets, and we have to, I don't want to say pull it back, but like we have to go backwards to the on the set level to talk about convergence of these functions on this complementary set that we're looking for. That's the best way I can describe what's happening here. So we start with this everywhere convergence, because up to some equivalence relation we can do that, and then we use this set definition of pointwise convergence. Okay, so all of x, so x is finite, right? Whatever. Pointwise, we can say that if these sequence of functions converge pointwise, then we can arbitrarily get close to them. And this notion of arbitrary closeness is measured here. Let me see what color my pen is. Maybe I'll just highlight. Okay? This is saying that no matter what, these sequence of functions, right, this is what it means to converge pointwise, is that we're getting arbitrarily close. We're getting these epsilon close in the codomain. Okay? So, but notice here that these are the set of x values. So now we're back in the domain. These are the set of x values where these functions are getting arbitrarily close to this measurable function. So now we have these sets of x, these set of x's that correspond to these sequences of functions, right? Okay. Now here's where we get into this lim sup and lim inf stuff that we talk about so much. Okay, so what does this mean then if we have the intersection of n greater than n? So, oh boy. When I look at this, I just immediately think lim inf, and that's, I can't even, not yet at least, I can't even give you a good way of remembering this. Just when you see union intersect, just think lim inf. Because we know, right, like if fn is going to x, if fn is going to f on all of x, then there has to be a way to write this in the lim sup lim inf set definition way. Like, and this is it. Because it's all of x, we just take we take the intersection, right, of all of these fn, and then we add them up or union them out. Okay. We call this the lim inf. It's also equal to if it converges pointwise, the lim inf of this and the lim sup will be equal. But okay, so now we're just going to let E and epsilon, right? E and epsilon just denote this set here. So we have this, like I said, we're going from the function level back to the set level. So we're just taking the set of x's where this works. Okay. Let's see. Okay. So how do I get that this is an increasing sequence? Like, okay, so like I said, right? It's a lim inf. I mean, it could be, I say limit inferior or greatest lower bound. This is not an increasing sequence. This is a decreasing sequence. I don't know why I wrote increasing. So maybe we'll strike this. I think because I want to do, eventually we're going to do a bounded from above argument, or a continuity from above argument, and so I wanted this decreasing sequence. But we're intersecting, look, we're intersecting a decreasing sequence. Like if we intersect this one and that's going to be contained, or that's going to contain the intersection, like intersections necessarily make things smaller, right? So we have this decreasing sequence, and then we're going to take the union, which is all of that of x, which the union of this decreasing sequence, which equals all of x. So that's the same as saying that the measure of x is equal to the limit of the union, the limit of the measure of the intersection of these, because this is the intersection. and it's a decreasing sequence. And then we know when I say continuity from above, page 26, it also might be page 25. I'm talking about in Fallen's Real Analysis book. Fallen's Real, yeah, I think it is called Real Analysis and Its Techniques or whatever. Okay. So by continuity from above, we have that this is true, that the measure of x is equal to the limit of these functions. This should be a lowercase n. Okay. So this limit exists because x is finite. The measure of x is finite. Okay. So we've used that hypothesis. Okay. So now let's take the complement. And I mean, the complement of this should be the empty set. Why? If this is equal to x, right, then the complement of this should be the empty set, or should eventually be the empty set. But what was I saying about this? Okay, so normally, and I haven't made this like rigorous or like general enough, normally when we're dealing with finiteness or like finite measure spaces, what I've noticed is that there's something called the complement trick, and it'll be like you are looking for something and you take the complement. So I mean, even in the statement of Ergorov's theorem, there's still this complement trick that's happening. Like something about finite measure spaces, even when you're dealing with like maybe even finitely supported measurable functions, or like compactly supported, or you're dealing with some sort of bounds or something, like you usually can take a complement of something, and then you'll see what I mean when we do more. But okay, so so now we take u on the complement of this, which is going to be u on x minus this, but we already know that this is limiting towards this one, right? This is, so it's going to be u minus this, that, and that goes to 0 because x can be written like that. Okay. Then for all k, we can choose an nk greater than n greater than 1, such that, now here's the part that's throwing me off. Because remember, I didn't prove this, I just copied the proof down and I'm going through it, and I've written so many versions of this proof. So now we take this is going to be less than x. I mean, it's for the same reason, because this converges here. Of course, we have, look, because this difference converges, we can bound it by epsilon. That's like the definition almost. The thing is that epsilon isn't big enough. We have to I don't mean big enough, I mean small enough. Like we have to make it small enough to guarantee that we stay away from something. Okay. Now some part use xk to denote the intersection, okay, as u minus x for all t, and note. So we're just relabeling because it's just, we don't want to write all these intersections, right? This should still, I'm still trying to figure out how we're getting this D set. Okay, so x minus the intersection of xk equals the intersection of xk complement, which equals the n xk, which equals x minus xk. But this should be, here's where I got stuck last time. Okay. See, let xk denote the intersection. xk denote the intersection. Which equals the union of xk complement. But what is xk complement? Like what? Which equals the union of x minus xk. It follows that yes is equal to, okay. I'm just trying to figure out, so you see here, before this was like this, it was written like this, and I wasn't sure if that was a typo or not. So, then D is measurable, and the measure, But like, how did we just construct this? Because it looks like we did like the same, I guess because it was point-wise, but like what? Okay, it remains to show that F angles to F uniformly on D complement, which equals the intersection of the AK of the XKs or XK. So it's an intersect of an intersect. Okay. In fact, for any integer m greater than or equal to 1, note that xk is contained in x. Yeah, it's a decreasing sequence, yes. Again, it's like the same thing as we did here. So we did here, like this one will be contained because we're intersecting, so it gets smaller. Or it stabilizes or whatever, but yeah. Let me show. In fact, for any integer, yes. Thus, for any x in here, we also have the x's in the m greater than or equal to 1. Yes, okay. According to the definite reaction, for any m, we have what? And that's the proof. All right, great.